So today is the fourth week, and we're gonna talk about something really important in AI engineering, which is about building a vector database. I think this is probably one of the favorite subject as well for you, Bernard. Vector databases, and like we'll go start from the fundamentals and the need for vector databases and embeddings and why you need them. Um, it's a this is a very like a very large concept. It's quite broad. So, but I want to try and like figure out like what are the fundamentals and then try to sort of go and build a very quick vector database to show how that can be done. So we'll go through a lot of theory today, but if there are any questions, feel free to add them in the chat if something is not clear. But the general sort of outcome is from today's session is to understand what are embeddings and what are vector databases and how we can sort of interact with them and how we can create vector databases. So that's the focus for today's session. Um, so as I mentioned earlier, we'll sort of look into fundamentals of embeddings and what are they and why we need them, basics of vector search, and why vector databases matter and why we are building them. And we'll also build very quick vector database using FAISS, which is like open source library that you can sort of build a vector database locally, and also using Pinecone, which is like a managed service. That means you can sort of provision the entire vector database in the cloud, and it's quite production ready. So you can use that if you have a sort of ongoing project that you're going to play around with. And then we'll also look into some of the popular vector databases and tools that you can sort of to interact with vector databases as well as to understand embeddings. So that's the focus for today. So I think we need to start from like natural language processing, right? Um, so the concept natural language processing, the idea is that you try to understand text, the written text, whether it's like a sentence, document, so you that's the whole concept behind natural language processing, the language that humans speak and how you sort of process them in a way that the computers can understand. So the question starts like, why do we need to convert this text into numbers, right? So why can't we just process them as text? But the issue is that computers only understand binary ones and zeros or just numbers, and because of that, we have to convert sort of text into representation that is understandable by the computer. So that's why we sort of convert text into numbers. And there are quite a few other advantages by doing this. Like, for example, you can do mathematical operations to identify similar text groups, to cluster them, to classify. So having them in text format is quite important. It's quite valuable, and you can scale like so because there are quite a few um, features within databases that you can do like large calculations, distributed calculations. So because of that, having them in number format is quite easier. Like for example, vectorized calculations, etc. And then to have consistent um, storage. So you know like what's the actual sort of text representation, and you can sort of zip them and transfer them. So you can do quite a lot of calculations around um, the text they're looking at in a more consistent way. And also, if you look at almost all the ML AI fundamentals are based on like modern AI models are based on like numeric representation. So because those are the reasons that sort of make the case for making text, the natural language processing in numbers. So on the right hand side, there's example how you can sort of convert like what like a numeric representation of a text looks like. So the word dog, it's an array of numbers. So in real life, it would be like in a real embedding setting, this would be not like four, it won't be just four numbers, it would be like long string like 500 or 1000. So depending on the type of the embedding model that you're using, based on that, you'll have sort of a string of like float numbers to represent what the text looks like as an embedding. So this is a vector and like vector of like four uh, vector size of 4. And you can also convert puppy is another word, and you can see like this close the each position, for example, 0th index is quite similar, so 0.12, 0.15. 0.98. So there's quite a bit of similarity between these two words. So if you have like a different word, you see the differences between those two. So these embeddings are generated in a way it represent the contextual meaning of this word. And so similar words or similar sentences would have close numbers. So because of that, you can identify familiar and close sort of numbers, close words together. So it's quite helpful if you're doing a similarity search, clustering, things like that. So that's why you sort of convert them. And then when you convert them, you need to embed the context into these numbers. So that's what happens in a sort of a transformer model where you sort of first tokenize them and then you embed the contextual information to these numbers so that the text embedding would be able to identify similar words within that corpus of data. So this is like the reasoning for sort of creating text to numbers. So in the past, so word embeddings um, can be done in like quite a few ways. So in the past, you had like traditional word embedding mechanisms like TF-IDF, count vector, and then word to vec. These are still like commonly used methods in NLP sort of settings like word to vec, glove, and fast text. And the most recent sort of generative AI sort of uh, the breakthroughs have resulted in sort of these GPT-4s, llamas, the bird. So these kind of models that helps you convert directly text into embeddings, which with contextual meaning. So none of these methods in the past, maybe some of them have some level of contextualization, but it's not strong enough to understand the meaning between few words. For example, if you take the word bank, bank could mean river bank, but bank could also mean like the normal financial, in a financial sense, like the bank which has money. So if you use in a previous setting embedding, it will just convert to like a similar type of like a number. So you might not be able to capture that the different context, whether it's a bank, river bank, or bank with a financial setting. So that's the sort of the value that brings into play with like this contextual word embeddings like LLM based models. So it's quite important and quite valuable if we're doing so applications in the space. Um, so yeah, this is like the the types of categorizations of word embeddings. But I'll show a quick example to understand what this means. So, so text representation set up before LLMs, like I pick some examples. One is like let's take a sentence like dog plays with cat. And if you look at one hot encoding, this is like one of the common methods that you can sort of convert categorical variables into like a numerical form. It's used in quite a lot of traditional ML models. You sort of convert so for each categorical variable, you would have a column, and so this is like the column sorry, dog, and in that column you only have like one for dog because dog is there, and then for place you have another one representing that there's a value there, and with there's another one in the third position, cat being the fourth position. So you can represent using one hot encoding this word, but still this is just word by word capturing. Bag of words is another sort of popular method, and it's just to capture the frequency of each word. So dog is present once, place present once, with present once, but car is not there, so it's zero. If it's like one of the words in the dictionary, it is zero. So in real life, this would be like very long data sets, but just to example, this is how may it look like. So TF-IDF is a quite interesting one. So it's um, the tech frequency inverse. Actually don't remember the exact wording. So TF-IDF stands for text frequency. So the idea here is like trying to figure out um, what's you give a higher weight for values which are infrequent. So what that means is like, for example, if you look at words like with, place, are could be common within like a general sort of English dictionary, like those are used commonly. But if you look at like in a in the context of the problem, let's say if you have like thousands of documents, and in that, so you figure out like the word dog might be not that frequent throughout the document, but in this document it is present. So because of that, from that calculation you get a higher value. So it has some context in comparison to the main document, but words like with, place might not carry a lot of weight because those are quite common throughout the document. So in this way you can also have some level of representation, and this is a very common method in sort of natural language processing mechanisms. But this is in the past, right? This is like how we did in the word embeddings in the past. But currently, we sort of move into using sort of LLM based contextual embedding modeling. So, so this is what it might look like, right? So, so embeddings in general, like here, what I want to represent embeddings with contextual embeddings. So you it will be sort of a number that represent meaning. So dog might have something like this, puppy might have something like this, but the car might be quite different. So the first value is like minus 0.8, and third one is also far apart. So similarly, the values are quite far apart. So on the right hand side, you can see if you sort of map this, like it's not in. So I've reduced the values to um, two dimensions, but in actual setting, these are multidimensional vector spaces, so it's hard to visualize them. But for this use case, I've sort of visualized this in like sort of a two-dimensional space and sort of mapping, projecting all values to two dimensions. But the idea here is like in this position, the dog is here, puppy is here, and cat is also quite close by. But you can see the car is far apart, like so, because in meaning these two are quite apart because the embedding values shows that there's not much meaningful like semantic meaning between these two. So you'll sort of have embedding value that would represent that. So when you use like LLM based like a sentence embedding model to get these values for each text, you will have that number already generated automatically, and you will get this kind of value that sort of separate these two groups in a meaningful manner. So you'll understand why this is important. But for now, just understand the closest the words or sentences that are close but closer in meaning will be clustered together. The ones different has a different meaning will be far apart. So that's uh, the the feature of embeddings when we sort of generate them. So so this is like a good example for this, but I'll show this in code as well. But this is an output that I've sort of show this like the difference. So the first one is like keyword search. So you do like a match per match based on the actual keyword. Like you do a string matching, like if the value like that, if you take if you use the question, I need to sort of pull out the exact yeah, I think pull out I'll probably show this in the example. So I think the query I need to ask is, we go back to the code. Um, yeah, the query is CEO of Apple. So this is what's been missing here. So so let's say so you give a query like who is the CEO of Apple? You give this, and then you have sort of a array of values, and then you sort of compare them. So this is the first version, is that you use keyword search, where you look at, okay, the value of CEO is there, and then Apple might be there. So based on that, you get like a similarity score. But the issue with that is like the top hit is actually Sundar Pichai is a CEO of Google, which is not correct. But if you use semantic search, you will be able to get like, okay, the Tim Cook leads Apple as its chief executive officer, and then Tim Cook is the CEO of the iPhone maker. It doesn't even have Apple in it, but it has enough information to be able to sort of do a matching in a way that to show that Apple iPhone maker is Apple, and you can do that matching, and you can get like a very close by strings found from this search, but you don't have to have the exact word, like you sort of one-to-one matching, because the embeddings that we looked at, the numbers that we looked at would actually be able to find the meaning. So these are like long strings. So like these are like either 500 size. The vector size would be around 500 or 1,000 depending on the model that you use. But it is able to sort of easily sort of embed that information and find these like similarities. So that's the point I want to make here, that like semantic search is much better if you're finding like similar sort of strings or the words in the space. There's downside to this, like I mean, there's a cost to calculation, things like that. From accuracy point of view, this is like a really good use case. But yeah, um, not just text. I think I want to sort of highlight is that that you can use audio, videos as well, like any kind of a multimodal system, and you can sort of convert that to like these kind of vectors, and those would have like a similar meaning. Like for example, if you use like text models, like you can use like GPT models, or you can use sentence embedding models, and audio and video models. You would also have similar models. Like Gemini has like a multimodal model that you can use to sort of convert them to this kind of representation. So in that way, you can do much more complex calculations here, and just consider that as like sort of a vector and do mathematical operations. And find similarities, create vector databases, and things like this. So this sort of like opens up quite a few opportunities. So that's the value of embeddings. So I'll quickly show like this example I was showing earlier, this one, how this sort of operates and how it looks like in the code. So there are two examples here. Um, so so this is the first one is like semantic search versus keyword search. So I'll be sort of importing sklearn, which is a library, machine learning library that sort of has quite a few required methods like for cosine similarity. I'll explain what cosine similarity means in a bit, but just it's a way that you can find the similarity between two embeddings. And sentence transformer, which is needed to get a model that can sort of transform text into an embedding. This is sort of a transformer based model. You can get from Hugging Face. And yeah, that's all you need. And so how the code looks like, you have this like five sort of strings, and you have a query that goes see over apple. So we're going to try and see, given this data source, can we get a matching score for each sort of string and see what's the closest to our query. And so what it does is like first example is a keyword search. Um, you sort of figure out like, okay, what's the TF-IDF values, and then create like sort of an index based out of that, and sort of extract. So TF-IDF search method is here. What it does is like, so you vectorize that and sort of fit these values in a TF-ID F transformation, and do a sort of a cosine similarity there, and get the top, like depending on what's the number we provided, top three examples, and you get like from a keyword search point of view, what's the closest three items. But if semantic search, you have meaning in that. So what you'll do is like you use sentence transformer, which is a uh, sort of a transformer GPT based model that sort of extracts the normalized sort of encoded values, and then do a similarity search and get the closest values. So this um, will do the calculation for similarities, and based on similarity, you get the top, even this in the top three examples. And then you show the results. But I'll sort of run this and see if you get the same thing. Um, So it may take a few seconds. So so I want to show this. It should be similar to what I showed on the slides earlier. So this is the keyword search values. So it only managed to, like, yeah, this is the scores that it got. Like, so it might not be accurate. But if you look at semantic search embeddings, it has the Tim Cook leaks Apple. So Tim Cook is the CEO of iPhone maker. So you get all these values to the top. You can have that similarity because it's like embeds the semantic meaning in it. And even though there's no Apple in this, we should be able to get that value. I also have another example for embeddings here. So what this does is like, so this, I'll run this first. It's quite similar to what we did right now. So what it does is like, do a comparison between two words and then get like the similarity score. And then there's also sentence comparison for a query, who was the president before Trump, and then you get like these kind of like cosine values, and higher the value, higher the similarity. So I'll sort of explain in a bit like what this cosine similarity means, but also I've got a sort of a diagram drawn out of this. Let me see if I can show it very quickly. So this is what it looks like. So you got the words here, so the word cat, puppy, dog. So it's quite similar, but like in a dimensional setting, these two should be very close by. And other the sentences are like, who was the president before Trump, and Barack Obama was the 44th president. So you got these two sentences together. And there's another one: Apple announced new iPhone, and then the stock market fell sharply. So you have those values as well. Uh, but what I want to show here was like, so for the who was the president before Trump, the Barack Obama was the 44th US president, has like the highest sort of cosine similarity value. So that would give um the expected value in this case. And even this case, dog and puppy has 0.804 and dog and cat has 0.661, even though they have similarities, dog and puppy is the closest. So that shows like, you can have this semantic meaning embedded. So in this case, we're using a model named all mini LM L6v2. There are quite a few open source models. These are called sentence transformers. What they do is like they convert any kind of a string or a text into an embedding string. So you'll have a numeric representation with the context embedded. So you have like not just the value dog, and where dog sort of what sort of relationship dog has to other animals and in this setting. So that's quite useful if you're gonna do sort of a similarity search in the future. Um, so this is that example, and these are like all these are like generating the diagram visualization. But this is the most important part. So you'll do like find the most like the top three similar examples for a given sort of a sentence. So that's the similarity search in this case. Um, yeah, that's the example I want to show. And are there any questions? Yeah, yeah. So the comment. Yeah. Cool. I can take a question here. Like if there's a question before I move into actual vector databases, feel free to ask them. Gotcha. Yeah, yeah, it makes sense. Yeah. So there are different kinds of indexes that you can create and different kinds of sort of distance calculations depending on the type of data type, like whether it's text or multimodal. Yeah, valid point. Yeah, yeah. Really valid point. Yeah, thanks. So there's a question, Shrenik, do LLMs use similarity search for tasks like code generation or logic related tasks as well? Um, so LLMs, let's say it's not necessarily, I would say, similarity search, but you get embeddings, right? So if you look at like any kind of a LLM, how it operates is that so you have a question, and for that question, you predict the next output. So the question plus the context, you sort of transform them into sort of a embedding. So that's where you sort of get the numeric representation of the request, and you send that to the LLM, and in the output, you get another set of text that predicts the okay, for this text, this is the answer. So the question and answering type of LLMs. And then you get the output in embeddings, and then you convert that to text. So whether it converts like it will convert into text answer or the code. So that's how it happens. So I wouldn't say it's similarity search per se. It's basically like encoding and decoding the question and decoding the answer so that you get the output in so yeah, so that's how it happens. So like you get the question and then you convert that to embeddings, and those embeddings would generate the text, which is the code, in this case, code generation or logic, depending on that. So that's how the LLM sort of works. And this is like part of that rather than the solution itself. Does that answer your question, Srini? Cool. Yeah, actually, yeah. So I think like yeah, videos like you need to use like so I think the so what you're trying to say is like pixels are stored at embeddings, right? So the idea here is like I think you're referring to CNN models, which are not necessarily. I mean, it's a type of embedding, like you just convert images into text, right? So that is type of embeddings, but there are also like image models that convert them to like not necessarily RGB values, but like a different representation because it's similar to in the setting of the text we had like TF-IDF, like which are like just individual embeddings, individual pixel, and you convert that to some sort of like numerical representation. So, but you can use like image-based models that would capture the relationship between like other sort of pixels as well, right? So you might have like two parts of the image that are connected, and you need to store that information like which is closer to the other component in the image. So you sort of need to have like a GPT based image model that is able to like convert that into embedding. So that's slightly different to the standard like all the CNN models. And similar to videos, you'll also have like similar sort of representation when you convert into embeddings. And depending on the type of video model, so here like you could have like some sort of video model that sort of convert that to another vector embeddings model. So that's the distinction between these older version of numeric representation of something and like the current like the latest model which sort of embeds the contextual information into that. Hope that answers the question, Akshay. Yeah, cool. Okay, so let's go to the next section. I think this the next part is quite interesting. I mean, this is not the full picture. There's so much into this, but I think like this should lay the groundwork for you guys to go and implement this in one of your projects, do more research. Yeah, so we looked into this. So the next part is like vector search. So so in the past you might have seen like relational databases, right? So you get like SQL or sort of text-based like NoSQL databases. You may have all of this in your work like before the whole generative AI sort of explosion happened. But um, moving on from that, like you sort of got vector database. I mean, vector database were there, but it's not very popular because they had like very limited sort of use cases. But now, like almost like all the AI tools would have some sort of vector database, and you should know how to operate them within your sort of tool set so that you get the best outcome for your AI tools. So part of that is like vector search, right? So what is vector search? So you try to sort of find the closest matches for a given query, and then um, based on embeddings, right? So it's not a exact keyword search like a string matching, but you find the word using semantic matching by using meaning. So when I mean meaning, it could be like in a natural sort of English meaning, but also you can have like very specific relationship generated based on how you sort of structure the input data set that was used to create the model. So there are fine-tuned large language model, like fine-tuned transformer models that has like very specific relationships. So if you have like a very specific domain knowledge problem, whether it's in biology, chemistry, economics, you might have the like a very custom built data set, and you can use that to sort of fine tune the models. And based on that, this is a very common use case, by the way. So based on the specific use case, your sort of embedding model that sort of create the embeddings, which should be able to create embeddings that represent that relationship. So whenever you get an input, you will get output in embeddings, but that's not the normal sort of embeddings that you got from like a Wikipedia based model, let's say, but it can be very custom built model for your use case. But in this case, we're not sort of focusing a lot on these very specific fine-tuned models. Like here is like a example. You say query is cute puppy. Within documents, you can like it will also extract documents that has the word dog in it, even though it directly doesn't say dog. But the puppy is related to dog in English, so because of that you'll get the document that also has dog. So that's the general search, the task that we're trying to do here. So to do this, so you'll have the vector search fund, like different ways that you can calculate, like what I mentioned, there are like dot product, but also like there are other ways that you can do calculations, right? So the idea here is like you have two embeddings, so like you can see like these two dot, the red and the blue dot, like, so one could be the query, one could be another data point from the data store, like within the embeddings. I'll show that in a bit, like how it looks like. But the idea is like you try to find the distance between two data points, and one is one of the most commonly used one is cosine similarity. What you do is like you find the cosine angle, like the angle between two data points, and this is quite useful in a multidimensional space, that this value, this number makes sense, and this is one of the most commonly used ways. And also you can get like Euclidean distance, which is the direct distance between those two data points. You just um, find the distance between them, not necessarily the angle. There are two other ones like Manhattan distance, sort of the grid block distance, like this in this way. And I'm gonna butcher this name. I think this is Shubershow or Chebershow. It's a Russian mathematician. So he has this like distance between like a single axis. So this is quite useful in physics, etc. This use case. So you sort of find what's the projection of this data point to this one and find the distance between that. So depending on the use case, you need to pick the right kind of similarity measure. But 95 of the cases, cosine and Euclidean distance might be sufficient for your use case. So at the end of the day, what you're looking for is like closer vectors, meanings, like more similar meaning. Like, so that's the idea. And you do these kind of like mathematical calculations to find those similar embeddings. And that is what happens in a normal sort of vector database. Um, so, so this is how it works, right? So one of the ways is like you have these like um, embedding space, like each red dot means like a specific data point, and then you'll get like a query, right? So your query will have this is a blue dot which you're trying to find the closest match. How it happens is like you get a query, you convert that to an embedding, so like a string of numbers, like array of numbers, and then you do the calculation with the selected similarity measure, whether it's like Euclidean, whether it's cosine, it's up to you, and you pick that and you find the distance between each data point, and then you sort of like find, let's say if your target is like to pick the top three, you pick the top three with like the highest value and sort of return that back to the method that sort of called this, right? So k nearest neighbor algorithm is like one of the popular ones, but it's generally tend to do like a very brute force approach, so it takes a bit of time. So there are like ways to reduce time for this calculation. But the idea here is like you find k means like it's a number, so it could be three nearest neighbor, it could be five nearest neighbor. So the idea in k means like find like the top k values which are closest to the query. So that's the idea. And you give a query and then it will, so this is like an index actually. So you find the closest values and you return that to the user who asked this query. So that's how you like, if you look at like most of the um, like product websites, if you type something you get the closest ones. Like Amazon is one good example. If you type something you get something, so most likely they have like sort of vector search in the backend. I mean, and then based on that you can get the closest value. So this is a very valuable scenario when it comes to like AI applications, and also like things like similarity search, which is like recommendation systems. So this is a very important point, and like doesn't like, yeah, like the investment that is spent on this topic is going to be paying dividends. So like study this really well. So yeah. So, so the idea is like because that k nearest neighbor can take a lot of time to execute. If you have like a very large data sources, it's going to take a bit of time to get like a quick answer. It's going to be really expensive. So to do reduce the cost, reduce the time in finding the closest values, you tend to introduce different algorithms. So approximate nearest neighbor search. So the idea is like you are not like doing the full search. You do like a good enough search, right? So there are ways to do this. Like one is like you sort of use like an indexing system, so that sort of gives you very quickly where the closest values are. So you use sort of the IVF, HNSW, which are like a graph-based search system. So you have an indexing system that lets you very quickly find the closest values rather than directly checking all of them. So you have like pre-calculated values, so you can do that. Or then you can do clustering. Like for example, in this example, you may cluster these all of them together, and you have sort of an average value at some point, and you do the first the average value calculation to find the closest sort of cluster, and then you sort of return that cluster or find the top k values from that cluster. So that's another example. And you can quantize it. For example, embeddings tend to have this 500 or 1000. Um, like the size of embedding could be quite long. It's like dimensions would be 500 or 1000 plus. So you what you can do is like you reduce the size of that embeddings, like either get the average of that or like reduce it into like small numbers. And it will reduce accuracy, but at the same time, it might be good enough for your use case, and the calculation cost and the time reduced because of that. So approximate neighbor search would have um, something like that. You quantize the values. So quantization is like actually like reducing the sort of the sensitivity of the values. For example, if you take like one data point, it'd be like 0.8889, and like you have like quite a few floating points, you can reduce the number to like maybe 2 decimal points. So in that way, the number of operations that you need to do on the calculation will be reduced, and that's going to be quite helpful in like large data sets. So approximate neighbor search is like probably like a suite of um, tips and tricks that you can use to implement to have like a much more practical, efficient way of sort of doing vector search. And this is like used in like Pinecone, like other vector databases for you to sort of get the more practical outcome when you're implementing vector databases. So yeah. Um, yeah, so I want to like now try and show like how this looks like. Let me go and show you. So I have like two demos, like right. Let's see. So one is using FAISS. FAISS is like open source vector database created by Meta, Facebook, and it was used a lot early on. Meta, I'm not sure like if they moved on from that, but at least like a variation of must be used in like Meta's um, like most of their recommendation systems, right? And so FAISS is a library, and then we're going to use in a bit using Pinecone. But for this use case, what you try and do is like so there are a few steps in this, right? So you I'll run this and then I'll explain what the code does, right? So it may take a bit of time. So you need to install FAISS first, which is like a Python library. So the so the idea here is you sort of pick a model, like sentence, like a transfer model that helps you sort of convert text into embedding. So then you have set of text like you have dog, cat, car, and then you sort of encode this. So if you look at these examples, I've printed these values, the embeddings that we get, it will be something like this. So this is for dog, this is for cat, and this is for car. You can see it like there are three dots in the middle, so that means like these are like very large. Like there's so many values in between. Like I think this should be around maybe 500 or 300 something um like values per each vector. And then you sort of create the FAISS index. So FAISS is like a in-memory vector database. So you have within your code, and then you define like you get the dimensions of that, and then you get a using based on those dimensions, you create index. So index is the one that you normally use to do the search. So as opposed to like traditional databases, like we normally sort of interact a lot with the index of these like vector databases, you do the matching with the index, and then first you add these embeddings to this index. So what it does is like you have the embedding values and you have a pairing per embedding, like what is the actual value, and you get like sort of store that within this vector database. So this is the part where you sort of create the database and you make a query. So then you send the query that you have to get the closest value. So in this case, we are sending in WAN. So for WAN, the closest value we get is car. So this will get the top K value for this, and that is sort of presented here is car. If you let's say if you change it to puppy, it should be ideally bring dog. So yeah, so the match brings the dog. So likewise, you can check like can create very much more complex scenarios to get like the closest value, and this sort of opens up quite a few possibilities when you create like similarity searches and like especially rank systems as well. So yeah, this is the way that you do FAISS-based indexing and creating vector databases in memory, and this is the easiest way you can test out your idea. But in production setting, I would go for like a managed service mostly, which is like Pinecone. So Pinecone, let me see if I can find it. So Pinecone is a um, so it's a vector database, but it sort of managed by like another provider. You can just like create a vector database there and sort of connect your sort of application directly to that. It's very simple, as you can see. Like you import the library and sort of connect using your API key, and then you can sort of do RAG and multimodal search, semantic search. You can build quite a lot of products, and yeah, this is one of the ones I like mostly. But there are like I don't know hundreds of vector database solutions. VV8 is another one that's popular. I think you've used Quadrant at some point in one of the examples you showed me. So likewise, there are so many options to select from, but pick what you like and then sort of play around with it. Because each and everyone has their pros and cons, and you need to pick what sort of best works for you. But for our use case, I'll be using Pinecone, and I've already created an account, and I'll delete this maybe. This is something I've had, so I'll delete this. So first, it will take a bit of time because after you create this, gonna hit an error because I think I haven't had a sort of a um, interesting. Okay. Oh, no, 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 no. Okay. Okay. It needs to be simple. So we're creating index. I'll go to the code in a bit. What's the question we asked? Interesting. Let's see. Yeah, so for WAN it worked. I'm not sure why it didn't work for Puppy, but the idea here is like simple, right? So what you do is like so you create a Pinecone object, and then you create an index. The index is like in this case is like what is considered the database. Um, and so 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 on the Pinecone side, if you go here, you'll find the index here, and you can see the request that we made, right? Um, Metrics, like depending on like the calls that you made to this, like, and you can see like the database information here, and whatever the request that you made, you can find it here. So for example, for some reason, like, so when you make the call like WAN, so you can see the score for each index, like each value. So you get like for car, you get like 0.999. For the query WAN, and then for dog, you get like a very small value. So because of that, you get the top value from that search. So you can like try again, like let's say, what can we say? Not sure why puppy didn't work. Yeah, so you can get the best matches dog. So if you come here, so you'll see like a few more results here. Um, it's not loaded yet. Yeah, so this one, like, for the last three, for puppy you get like a score of 0.999 for dog, but like cat is like 6.66. So you get like the closest value, and you can sort of configure in a way like what's the index that you're using in this one, and you can get the closest matches for this one. So, but I'll go through the code right now, like what it's doing, right? So the first thing is like, um, create a index, which is the database itself on with Pinecone side, and then you create like a sentence transformer, and you get a set of text. In our case, dog, cat, car. So in like actual sort of LLM sort of like AI tool setting, you will have like larger, like documents, like larger documents, and then sort of embed this here using the model, and then you sort of upload this information to the index, which so it's called upsert normally. So you sort of upload the data to the database. You need to sort of, in this use case, you need to add some like time to sleep, because like it takes a bit of time for that to get set up. So if you sort of then query it, you're gonna hit some errors. So add like 2 seconds delay. And after that, I have a query called, I want to find the closest value for puppy, and then encode that, and then query it, like you get the index, which is the Pinecone object, and you query it using the embedding that we got, and you're asking for the top one, and then if you change it to two, you'll get two values ideally. I think I'm printing the top one here. Yeah, so if I look at what's the best match, yeah. So if I print the chart, matches, let's see what you get. Actually, we have the raw results, so I didn't see that. So you get dog score is 0.803, and the other one is like cat 0.53. So likewise, you can get like multiple values if needed. So the idea is like going back to what we discussed, we are getting the closest values per query, and you'll find that. So yeah, this is like simple sort of connection that you can make for Pinecone, and you can sort of directly embed this now in the application that you're building. Um, yeah, so just a couple more slides. Um, yeah, so I think we discussed, right? So um yeah, we discussed this part, but there are like different kinds of index types, like IVF, inverted file index, which is uses like a cluster-based algorithm, and HNSW, which is a graph-based algorithm. So if your problem represent like a graph-based, like a data set, you can use that, and product quantization, like if you need like memory efficient calculations, like for large data sets, you need to quantize the indexes, and then sort of use something, use a PQ type of index, so that it'll much more faster if you have like a large data set. The downside is the accuracy will go down, but it's quite useful depending on the use case. Yeah. So like where you'll use vector database, there's quite a few. Like there are rank solutions, semantic search recommendations, multimodal AI. And these are some of the like tools that you can use, like vector database tools that you can use. Like FAISS, we discussed the open source one, Pinecone fully managed. And there are a few more other, V8, Milvus, and I think Quadrant is another one, which is open source, but it also has a deployed version. So PG Vector is a one that is quite useful. It's very interesting. So that means that you have like a, within the relational database, you can have like a like an embedding column that can do like similarity search, etc. So if you use Postgres, like let's say either on Supabase, or you have like a your own sort of Postgres version of that, you can use like PG Vector, which helps you combine relational database with vector databases, and it's quite powerful, and it's really interesting use case. Um, and I want to show this very quickly, but before that, I want to touch base on what we discussed. Um, obviously fundamentals of embeddings. We discussed that, like how vector search works and what are vector databases and why we use them. We looked at a quick demo. I'll share the code base as well. And then some popular vector database tools, like vector database types that you can use.